What's up, everybody? It's Dan from Sage Math Tutoring, and here with a review sheet for a geometry test for a student of mine. Has a geometry test coming up, and let's go over some of the problems. So let's take a look. Name an angle bisector. Okay, so let's be clear about angle bisectors. The bottom line is, anytime they say angle bisector, like if the blue thing happens to be an angle bisector, immediately I would suggest you yourself drawing these little arcs here, okay? Because if it's the case that this blue thing happens to be an angle bisector of this black angle here, well, then this little angle has to equal that little angle. So when we're talking about angle bisectors, you want to kind of look for this pattern where there's this segment, ray, or line going through an angle, and then you have these two things being equal. And that is happening here. Okay. So you have this angle IGH, and this thing happens to be the angle bisector. So for my student watching, I think she understands that's going to be a GL, right? So that is this one. And notice how that is a ray, and that's what we're looking for. So the ray starts here, and then it kind of shoots in that direction. Okay, name a median. So the moment they're talking about a median, first of all, that implies the existence of a triangle. So we have a triangle. And remember, the median is a thing that would go from a vertex. So also going from a vertex, we could say, and then it cuts the opposite side in half. Okay. So median also has to do with a vertex such that it goes all the way through and actually cuts the opposite side in half. Now you have to be, savvy with how you kind of spot these because maybe the triangle looks like that. And in that case, you have to know that that sort of line there is a median, right? Maybe the triangle is positioned like this. And in that case, you would have to know that that's a median. Either way, this is sort of the pattern that you're looking for. And that is certainly happening with this. Let's take a look. That is certainly happening with this right here. Okay. This red one. Okay, because it's going from the vertex and it's cutting the opposite side in half. So that is HJ, something like that. Yeah, right there. Okay, name and altitude. So let's remember, I know my student watching is used to altitudes being the so-called height of the triangle, but rather than thinking of the height of the triangle, I'd rather everyone think of it as dropping down from a vertex in such a way that forms 90 degrees with the other side. Okay. So notice how, once again, the vertex is important. The segment that we would call an altitude kind of emits from the vertex. Now, the reason I'm harping on that is because there's another concept, okay, called perpendicular bisector, where maybe this thing had been cut in half and you have this thing go up like that. Now, that is a perpendicular bisector, but that is not an altitude because for it to be an altitude, it has to go through the vertex. So this is an altitude. Now, I'd rather people think of altitudes in that manner because if you think of it as the height of the triangle, well, then you're always going to need it to be positioned upright like this. But the reality is even if you turn the triangle like that, well, it's still an altitude. And even if you turn the triangle like this, it's still an altitude, that blue thing. So where's the altitude? They're asking for the altitude. Well, first of all, we should be on the lookout for the 90-degree symbol and something that goes through a vertex, right? So we have certainly a 90-degree symbol here, but this thing does not go through the vertex, right? Now we have a 90-degree symbol here, and this thing does go through the vertex. So we're happy with that. That is most definitely an altitude because that checks the boxes. So that's IK or KI, right? So that's right here. Okay. Now name a perpendicular bisector. Well, I had already talked about that. Um, Perpendicular bisector, yeah, it's going to have 90 degrees, but it's not necessarily attached to the vertex. And the thing to know about perpendicular bisector is that yes, it forms 90 degrees, but it's also cutting that side in half at the same time. So that's the pattern you need to look out for when it comes to perpendicular bisector. Now we have a 90-degree situation here, and it's cutting that side in half. So it is really this green line that is indeed a perpendicular bisector. So what do we call that? Well, the only points mentioned are this J point and this M point. So that's going to be line JM. So you do have to be savvy with spotting that. That's right here. Okay. Looking at problem number five's directions. Refer to the figure to determine which is a true statement for the given information. Okay, so we'll take this off to the side. So we are referring to this diagram here, right? This thing is saying WY is an angle bisector. Okay, so what they're saying is if this is true, what else must be true? So for my student watching, we already did this today earlier, but if this is true, if they tell you, oh, it's an angle bisector, then I would immediately throw these labels on it, right? That's kind of what I said before, because just based off of this blue information, we know that the yellow things are true also, right? Now that means that angle XYW is the same as the angle ZYW. And that is communicated right here. So that's going to be the answer. All right, so that's that one. Looking at the number six, YW is an altitude. All right, so now they're saying that this thing is an altitude. Well, the moment they tell you something's an altitude, you know what I'm going to do? I'm going to drop a 90-degree thing on that. Because if the green thing is an altitude, well, it's already going through the vertex. What's the other feature of an altitude? The 90-degree situation. So what do we know? We know that angle XWY is 90 degrees. We could also say that angle ZWY is 90 degrees, aka a right angle, or ZWY, yeah. Um, okay, so this is saying YWZ, which is the same as ZWY, because we could have gone backwards, ZWY. We could have gone backwards with that. So this is the one that's correct here. Okay. Mm-mm. Looking at this one, YW is a median. What's a median? A median is such that it goes through a vertex, but in such a way that cuts this other side in half. For my student watching, not to be confused with perpendicular bisector. If it was a perpendicular bisector, there'd be a 90-degree symbol here. Also, perpendicular bisectors don't need to go through vertices like this, but medians always need to go through a vertex. So in fact, you could start from the vertex, cut across in such a way that cuts this in half. So what do we know? XW is equal to WZ. So that's right here. Okay, hopefully that makes sense. Those are the answers to those. Um, this over here is a barrel of fun. Get rid of a few things. Okay, name the longest side. Okay, should be easy for my student. The longest side is the side that happens to be across from the largest angle. The largest angle here is 84, so the longest side is AB, aka BA. So that's this one. Name the angle with the greatest measure. Well, the angle with the greatest measure is going to be the one that's across from the longest side. The longest side is EF. The angle that's across from EF is D. So that's this one. So for this one here, which theorem compares the sides of the same triangle? Hmm. Um, that's going to be the triangle inequality theorem. Okay. So the triangle inequality theorem, let's just answer it. Let's talk about triangle inequality theorem. We'll talk about all of these real quick. Okay. We're going to talk about all these because that's just a barrel of fun. Just so we know, when they're even saying these, what do they even mean? So, the triangle inequality theorem essentially says that the length of one side must be less than the sum of the other two sides. So, in other words, if you have a triangle here, this is side A, this is side B, this is side C. We might not know much about C, but we know that it has to be less than A plus B. We might not know much about side B, but we know that it has to be less than A plus C, and we might not know much about side A, but we know that it has to be less than B plus C. So that's the triangle inequality theorem. Notice how this has us just comparing the side lengths within the same triangle. Okay, now that is what they're asking. They say which theorem compares the sides of the same triangle. So that's why this is the answer. Now, we should talk about the hinge theorem. Basically, the hinge theorem says that in two triangles with two congruent sides, the side opposite the larger angle is longer. So what does that mean? Well, imagine you have some triangle here where that's 3 and that's 4. And then you have another triangle where that's 3 and that's 4. And this angle is, let's say, 70 degrees. And this angle right here is 35 degrees. Well, which do you think is a longer third green side? Um, or a third side, rather. Do you think it's the green side or the red side? Well, most people would agree that this green side is certainly longer because it's across from this 70-degree angle. This red side is going to be shorter because it's across from the 35-degree angle, which is a smaller angle, right? So notice how the hinge theorem is pretty intuitive, right? And also it compares two different triangles, okay? So let's go to the converse. Now, the converse would always kind of say the opposite. Okay, so let me just kind of do this right now. Um, so notice how in the hinge theorem, we didn't know how long this green one was necessarily right away. We just knew that it was longer than whatever this red one is, right? Now, in a similar fashion, you can kind of go in the opposite direction where, let's say, for example, you actually did indeed know how long this green side was. Maybe it's 6 units long, and maybe this is 2 units long. Well, right away, because this yellow thing is congruent to the yellow thing, because this blue one is congruent to this blue one, we know that since this side is shorter, this angle has to be smaller than this angle. Okay, so it's just the opposite reasoning. So that's that. Exterior angle inequality theorem. So for my student watching, hopefully she recalls, we might not know much about this blue angle, but we definitely know that whatever that blue angle is, which is on the exterior of this triangle, we know that it has to be larger than this remote red angle. We also know that this blue angle that's on the outside of the triangle, leaning up against the triangle, has to be larger than this far away angle also. Okay. Now, my student watching might remember this blue angle is actually equal to the sum of these two. But then, doesn't it make sense that the blue angle would be more than the red one? And blue angle would be greater than or more than the yellow one. Okay, so that's the exterior angle inequality theorem. Now, again, this question is saying which theorem compares the sides of the same triangle. Well, we're not comparing sides here, we're comparing angles, so that's why that's not the answer. Okay. Tisha wants to plant a garden in the widest corner of her triangular backyard. Here's a triangular backyard. Here's the back of the house, um, and that is 50 feet. Um, Fence A, okay, that's fence A, 27 feet. And then fence B, 35 feet. And they want to know which corner has the widest measure. Well, it's the one that's across from the longest side length. So that would be this one. So it's at the corner of fence A and fence B. So that's this one. All right. Really easy. Just got to draw it. Okay. Find the possible values for the measure of angle 1. Well, due to the exterior angle inequality theorem, angle 1 has to be more than 74. So where is that mentioned? The opposite is mentioned here. It says that the measure of angle 1 is less than 74. So that's gone. This is some gobbledygook that doesn't even mention the relationship between angle 1 and 74. So this is suspect, okay, to be wrong. Over here, this is saying that the measure of angle 1 is bigger or larger than 74. So I do agree with that. So that's a possibility. And this is saying that the measure of angle 1 is larger than 74 as well. So that's a possibility. So now let's investigate these because these are the most tempting. Now, before I do so, imagine for my student watching, I kind of explained this earlier, but I want to make sure that this is very clear. Imagine that we took this angle, this blue angle, and we actually like made it bigger, where it widened and we kind of pushed like a hinge this side down. We kind of flattened it down. And then eventually, if we flattened it all the way down, right? So that angle 1 was, this 180-degree angle. Well, we wouldn't even have a triangle anymore because this whole thing would have gotten smushed down and it wouldn't even be a triangle anymore. Okay, so hopefully that makes sense. I'm trying to do this like animation kind of a thing where basically this side goes down. So I think my student probably gets that. If you push this side all the way to the floor and form 180 degrees here, well, guess what? No more triangle. So we might not know much about this blue angle, but we know for sure that it's less than 180 degrees. And that is why this answer right here is the correct answer. Because once again, the measure of angle 1 certainly needs to be more than 74 because of the exterior angle uh, inequality theorem. And then it also has to be less than 180. There's no question about it due to the thing that I just said. So let's move on with our life. Looking at 13, find the value of x. Hmm, okay. So um, any time you have some segment that's being cut in half, but not just cut in half by any old thing, cut in half by this sort of line that forms 90 degrees. So that red line is a perpendicular bisector to the black segment. And let's say that's the situation. And then for entertainment, you decide to just plot a point anywhere on that red perpendicular bisector line. And maybe because you were bored, you decided to connect that random green point to one of the end caps and connected it to the other end cap. Well, it turns out that that would make it, or that would be such that this yellow thing is equal to that yellow thing. Okay. It's like the perpendicular bisector theorem. So, perpendicular bisector theorem says those yellow things would be equal to each other. So really, you need to just be clear. Whenever you see this pattern, it means these are equal. Okay. So then this is the pattern here. We have a perpendicular bisector. Clearly, so what that means is that this whole guy has to equal this whole thing. And my student earlier did it really well in that she recognized she could literally just set them equal to each other. We have x plus 2 plus x plus 7 equals 27, 2x plus 9 equals 27, 2x equals 18, x equals 9. And yes, we have to be careful. We are indeed asking for x, therefore it is 9, and we are actually done. Which of the following sets of numbers can be the length of the side of a triangle? So we know that each side has to be less than the sum of the other two sides, but it also has to be greater than the difference of the other two sides. So is 6 less than the sum of 6 and 12? Absolutely. Is 6 less than the difference between 6 and 12? No. So this cannot be a uh, triangle. This 6, is this 6 less than the sum of 7 and 13? Yes. Is this 6 more than the difference between 13 and 7? No. And for that reason, that's not a triangle. Um, if you were to do this in the calculator, um, radical 2, first of all, is approximately 1.41-ish. Radical 5 is approximately 2.24-ish, and radical 15 is approximately 3.87-ish. Um, so I will investigate radical 2 first. Is radical 2 less than the sum of these? Well, yes, certainly. Is radical 2 more than the difference of radical 15 and radical 5? Well, when I do the difference of radical 15 and radical 5, I get 1.6 something. And radical 2 is not greater than that difference. We want radical 2 to be greater than the difference. So this is gone. Okay. Looking at this, is this less than the sum of these? Of course. Is this less than the difference of these? Or is this greater than the difference of these two? Uh, it is. Okay, the difference of these would be 2.1, I believe, and 2.6 is indeed greater. Okay, looking at this one. Is this one less than the sum of the other two? Yes. Is this one less than the difference of 10.2 and 2.6? Um, is this thing greater than the difference? Well, 10.2 minus 2.6 happens to be 7.6, and this is certainly greater than that, so we're happy. Uh, is this less than the sum of the other two? Yes, it is. And is it greater than the difference of the other two? Yes, it is. So this can be a triangle. Okay. What's the relationship between the lengths of QS? Okay. And RS. So we'll make QS green and we'll make RS red. Now, what's the relationship there? I would have my attention drawn only to this yellow triangle, and I'm going to kind of draw that off to the side. That is this. And we're trying to compare this red one to this green one. And they're also telling us that that's 90 degrees. Now let's forget this whole T part and just look here. It's the case that this is 90 degrees. Now that guarantees that this is the largest angle out of all of these. Because think of it. Let's call this angle measure X degrees. We'll call this angle measure Y degrees. Hopefully, we acknowledge that angle R plus angle Q plus angle S equals 180. Well, angle R, we already know what it is. It's 90 degrees. Angle Q, we're calling X, and angle S, we're calling Y. Okay. So for my student watching, hopefully she could recognize that we could indeed subtract 90 from both sides. Then you would have X plus Y equals 90. Now, what does that mean? That means that we don't know what X is, but we know that it has to be less than 90 because X plus something else gives you 90. We might not know what Y is, but we know that Y has to be less than 90 because Y plus something else would give us 90. So in short, this angle is certainly less than 90, and this angle is certainly less than 90. So this angle is certainly less than that angle. This angle is certainly less than that angle. What does that mean? That means this is the largest angle in the whole triangle, and that means that this is the longest side. Now, what does that mean? Well, that means this is longer than this one, and that's all we need to know. So let's take a look. Um, QS is certainly greater than RS, so that's this one. Okay, so that's how you do that. Now, do you have to write all this? Absolutely not. For my student watching, I'll just say, go ahead and memorize the fact that if you have a triangle and it's a right triangle, that 90-degree angle will always be the longest angle or the largest angle in that triangle. Okay. What is the relationship between the lengths of DC? All right, and AD. So DC will make red. AD we will make green. Okay, this is the hinge theorem. So um, we can separate the triangles and remind ourselves of what the hinge theorem says. Now, this blue thing is 10 in, in one second, A, B, D. This, by the way, is B, C, D. Now, this happens to be 10 as well. Now, we don't know anything about this yellow side, but we know it's equal to this yellow side because it's shared. Okay. Now, this is hinge theorem. Once again, hinge theorem says that if this side is congruent to that side and this side is congruent to that side, then you can compare the black sides depending on how big this angle is in here. Okay. Now, this angle is 20, and this angle is 30. So because the blue is equal to the blue, the yellow is equal to the yellow, this angle is bigger, so that means that DC has to be bigger than this DA thing, okay? So in other words, this red one has to be longer than this green one. So DC is longer than AD. That is right here. Okay, hopefully that makes sense. Looking at this one here, what is the relationship between 1 and 2? It's probably a hinge again, where the blue side is equal to the blue side. And we'll make this yellow again. The yellow side is squared. Now, this angle is kind of creating or giving birth to this longer side. This angle, angle 2, is in a sense opening up to or giving birth, we could say, to this shorter side. So that means that angle 1 has to be greater than angle 2 because angle 1 sort of is related to this longer side. Okay. So angle 1 is greater than angle 2, and that's this one right here. Okay, name an angle bisector. So an angle bisector, once again, we know what pattern we're looking out for, hopefully. We have this thing going out of the vertex, but by the way, we can draw these little things. That's an angle bisector. Where do we see that pattern? We see that pattern right here, right? Because of these yellow little things. So the angle bisector, now they want us to name it. It's not multiple choice anymore. So now we need to be on our game. Uh, the ray in this case is ray AD. Okay, ray AD. Now, I have a feeling for my student watching, the teacher might be a stickler for you putting the ray symbol here. Notice how the ray emanates from point A and then it goes in this direction forever, right? So that's why we should write ray AD like that. So once again, I have a feeling the teacher might harp on that. Um, Problem number 2, the perimeter of ABCD, which is this thing, is 44. Find the value of x, then describe the relationship between AC, line AC, and BD. Okay. Yeah, I can see where this is going. This is going to be an angle bisector kind of a thing, probably. Now, the perimeter of that weird blue boomerang shape is 44, but my student earlier today did a good job recognizing that that could be found by adding all the sides, you know? So we have x plus 1 plus 2x minus 3 plus x plus 5 plus 2x minus 7. We have like term, 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 like term. The green like terms turn into 3x, 4x, 6x. The yellow underlined like terms turn into -2, plus 5 is 3, minus 7 is -4. It is the case that we can add 4 to both sides. We end up with this 48. X therefore equals 8. So we found X. That is one of the first things they wanted us to do. Now, they want to know what's the relationship between line AC. Now, notice the line symbol here. That's important. What they mean is, yeah, I know C is here and A is here and everything, but they're talking about this entire line, are they not? They're talking about that whole line, and they want to know what's the relationship between this yellow line, right? AC and this red BD segment. What's the relationship between those two? Well, I feel like I can already see where this is going, so let's remind ourselves. Imagine you have a segment minding its own business. We'll call it AB. And imagine you obnoxiously cut through it like this. And you know that this is the perpendicular bisector. Okay, now what does that mean? The yellow thing is the perpendicular bisector. What does that mean? Well, it means that this is perpendicular. This is 90 degrees, but it also means it's a bisector. It just cut this AB thing in half. Okay. Now, once again, as hopefully my student recalls, you can pick any point on here, and then just because you're bored, choose to um, connect the endpoints from that point. So if you already know that the yellow thing is the perpendicular bisector of this black segment, then you know that these have to be equal to each other. That's the perpendicular bisector theorem. Okay. Now, the converse is true as well. Now, what do I mean by that? Well, imagine you have a segment and you have this obnoxious thing cutting through, but maybe you don't know yet if it's 90 degrees, and maybe you don't know yet if it's cut in half. But here's what you do know. You know that there's some point here, and these green things are equal to each other. That's what you know. Well, then by the converse of the perpendicular bisector theorem, then you can know, oh, okay, so this is 90, and these have to be equal to each other as well, aka if the green guys are equal to each other, then the yellow thing is the perpendicular bisector of the black segment. Okay. So that is what I think we're supposed to say right now. Bottom line is, if we can prove, let's make it purple. If we can prove that this purple side is the same as this purple side, well, then we know this yellow thing is the perpendicular bisector of this red segment. And then we could say that. So we just have to prove that the purple things are equal to each other. Well, we already know that x is 8. So what's that? That's 2 times 8 minus 3, aka 13. This is 8 plus 5, aka 13. So yes, they both equal each other. Therefore, you could write down that line AC is the perpendicular bisector of segment BD. All right. All right, looking at problem number 3, if point E is the centroid of ABC. Okay. So they're talking about centroids, which makes me want to get my handy dandy table in front of me, and that would be this table or something like that. That sort of reminds me of all the different things, points of concurrency. We have the circumcenter that maybe we should be aware of, the incenter, centroid, orthocenter. Obviously, we're dealing with this one. All right, so they're talking about centroids. Let's remind ourselves of what that even means. Well, first of all, the centroid is formed when you draw the medians everywhere, right? So a median, once again, starts at the vertex and then cuts the opposite side in half. Well, of course, you could do that on over here as well, right? And you could also do that over here as well, right? So it's going to get messy, but it is what it is. So this purple point is called the centroid. All right. Now, for my student watching, you might remember that this is that whole 2/3 thing, okay, where it's like, or 1/3. Like if we were to literally just analyze this purple one here, well, it's the case that this part, this longer part, happens to be 2/3 of the distance all the way across the purple thing. Okay. And that would make this 1/3. Okay, so that's 1/3 of the whole thing, and this is 2/3 of the whole thing. Now, that's a beautiful thing to know that will come in handy occasionally, but once again, for my student watching, you probably remember me saying that I like to, whenever it's a centroid, I like to just think of each of these medians such that you can kind of divide it into like three equal pieces. So we have this piece, and then if you divide that in half, we have this piece, and this piece, and they're all equal to each other. Okay, so I don't know what we could call that. We call that X, but this is also X, and this is also X. Okay, to me, that ends up being a little bit more useful. All right, so let's see what they're saying. BD is 12. Oh, okay. Well, check this out. As soon as they say that, I'm going to obnoxiously do a thing where, oh, okay, it's all 12. Fine. That's 4. That's 4. And that's 4. Am I wrong? Feel like I'm right about that. Okay, EF is 7. Oh, okay. EF is 7. Okay, got it. 7. Oh, guess what? This is 7. And then this is 7 also, right? And then AG is 15. Oh, that's the small part right here. That's 15. Okay, cool. 15. Okay, guess what? 15. So we get these purple 15s. Yeah, so I feel like I just labeled that amazingly. So find ED. Oh, what's ED? ED is 4. See, we already finished it. We already labeled it. We're good. Yeah, I guess that's it. Is that all we have to do for that one? All we have to do. So I don't even know if I needed to label the other things. I think the only information we needed was from the BD. Am I wrong? Yeah, so all this might have been a distraction. Oh, that's crazy. Anyway, hopefully my student recognizes ED clearly for. So, hmm. Okay, we got vertices, which makes me not happy. Hmm. Yeah, okay, so that is not fun. Um, X is at -2, comma 6. That would put it around here. Y is at 4, comma 10. That will put it about here. That's a Y, by the way. Z is 14, comma 6. Okay, the fact that that's the same Y coordinate as this one makes me happy. So let's imagine drawing this triangle. Clearly not drawn to scale. So if they're asking for the coordinates of a centroid and it's such that you're plotting it on the XY coordinate plane, the good news is believe it or not, you only really need to analyze one median. You don't have to go on this mission where you're drawing all the medians and then, oh my God, now I got to find out where they intersect. That would take a very long time. The good news is you do not have to do that. Um, you only need one median and you only need to analyze one median, and that's what we're going to do right now. Okay. So, um, you can imagine that there's a midpoint here, and that should be a relatively easy midpoint to find, because that is going to be halfway between 14 and -2. Now, anytime you want to find sort of the midpoint between two numbers that are like across from each other like that, like in this case, -2 and 14, you just add the numbers and then divide by 2. So -2 plus 14 is 12, and 12 divided by 2 is 6. So this thing corresponds with 6. So hopefully my student watching recognizes that the coordinates of this are 6, comma 6, right? We already knew the y-intercept or the y-coordinate of this point, right? Now, this is why I chose to find the midpoint on this bottom part, is because I saw that the y-coordinates were equal to each other, which means that this y-coordinate is also going to be 6. And that just makes our life a lot easier to find the midpoint here. Anybody might be wondering, why am I finding the midpoint? I'm finding the midpoint because we need to analyze a median. Well, what is a median? A median is that special little segment that would connect the vertex to that midpoint, right? In such a way that cuts this in half, right? So that's a median, right? Now, let's remind ourselves of something. The midpoint is right here, right? And the short part is close to that, whereas the long part is close to the vertex, right? So if we were to kind of think about that, that would mean that the long part would be here and the short part would be, this green part, right? So that's an interesting observation. So you might be wondering, how does that help? Well, let's just analyze this median, maybe off to the side, because it's already starting to get a little messy. But before I take this median off to the side to analyze it, hopefully my student watching recognizes that the centroid is going to be here, isn't it? And that centroid is going to be 2/3 of the way down to this part. So once again, let's go off to the side and just analyze the segment without all the extra noise. Okay, I'm just going to transfer the information over here, only without all that other stuff. And we know, once again, that the centroid's going to be like there. But the question is, what is, what are the coordinates of that thing? Well, one way of going about it is you can note the difference between the x values and then note the difference between the green y values. Now we're going to do something interesting. We're going to say that the x coordinate of this centroid, that x coordinate is going to be 2/3 of this difference plus this. So in other words, we're going to find the difference between these x coordinates. We're going to find out what 2/3 of that difference is, and then we're going to add it to this one. All right. Now, for my student watching, I actually have the suspicion that this is the problem that your teacher's not going to expect you to do on the test, because I can already see this is already getting a little crazy. But see if you can follow this, okay? This might be a bit advanced, but just hear me again when I say what I just said, okay? I'm going to repeat that. So we can find the difference between the x coordinates. We can find 2/3 of that difference. And then whatever that is, we add to the 4. And that brings us to this x coordinate. So let's do it. It's going to be the x coordinate of 4 plus 2/3 of the difference between 6 and 4. I know that's a little crazy, but once again, we're finding 2/3 of this difference. That's right here. And then we're going to add that result to the 4. That's here. So 4 plus 2/3 times 2. 2/3 times 2 is 4/3. Okay. 4/3 is really 1 1/3. And 4 plus that is clearly 5 1/3. Okay, so that's right here. Now think about it. Doesn't that kind of feel correct? Okay. What is the coordinates, the x coordinate of the centroid? Well, it's somewhere between 4 and 6. It's 5 1/3. Okay, it's 5 1/3. So it will be the same process for this. Now, let's make a note. When I said the difference between the x coordinates before, I took the x coordinate of the rightmost point and I subtracted the x coordinate from the leftmost point. This point is slightly to the left of this point. Well, it's going to be the same thing. So when we do 2/3 of the difference, it's going to be the y coordinate of the rightmost point minus the y coordinate of the leftmost point, and we will be eventually adding that to the 10. Okay. So we have 10 plus 2/3 times -4. That's 10 plus -8/3. That's really 10 plus -2 and 2/3. That's really 10 minus 2 and 2/3. And that's really 7 1/3. So that's this. Now, let's think about it. Does that feel correct? Well, this y coordinate, whatever it is between 6 and 10 somewhere. And it's only like a little bit above 6. And yes, that is correct. It's 7 1/3. I don't know a better way of doing that. I hate to say it. So for that one, for my student watching, just be on the lookout for this one to not be one that you have to do. Um, there's a lot going on there. Okay, but I feel pretty good about the answer. So that's that. Problem number, what are we doing? Oh, 5. So let's bring all this down. Angle bisector, okay, of MON, find the value of X. Oh, well, if it's the angle bisector, right? This blue thing is the angle bisector. Well, what have I been saying from the beginning of this video? Make this angle equal to that angle. Therefore, obviously, 2x minus 10 equals x plus 15. This is like so easy compared to the one that we just did. So we have x equals 25 done. And they are asking for x. So, oh, exterior angle theorem, maybe? Hmm. Biker will jump over a ramp where x and z are measured in feet. Okay. Write an inequality relating x and z. Well, well, even if we don't know exactly the path to victory here, um, let's be clear. They want us to write not an equation that features z and x, but they want us to write an inequality that features z and x. Now, in order to do that, we probably should take advantage of some of the theorems that we've been dealing with. First of all, according to the exterior angle theorem, this 165 angle here, this red angle, that has to equal this thing plus that thing. So hopefully my student watching understands that's enough information to find this right now. 165 minus 70 is 95. So this is 95. Okay. Now, if that's 95, we can find this by either recognizing that this angle add up to 180, or as my student watching might recognize already, this angle is a linear pair with the 165. So 165 plus whatever this angle is would be 180. So therefore, I think we all can see that that angle right there is 15 degrees. So, yeah. Therefore, the largest angle is this green box 95 angle. And what that means is this has to be the longest side. So what does that mean? That means that this side is longer than this side. Well, that's like an inequality that we could write. We could write, okay, cool. 2z plus 3 is greater than x over 5, right? The green side is longer than the yellow side. That's what we're communicating right here. And we're done because all they asked us to do was to write an inequality that relates x and z. Well, here's your x, here's your z, or z. Here's how they relate to each other. I think that's all we need to do. Okay. Mm, list the angles of blah, 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 blah in order from smallest to larger. I mean, obviously, come on now. The smallest one I'll call 1, the medium one we'll call 2, and the largest one we'll call, well, no. The smallest one we'll call S, the medium one we'll call M, and the largest one we'll call L. How about that? So, smallest one, well, that's this one. Come on. S. The medium one, clearly this one, and the largest one, clearly that one. So if we want to list the angles, that's angle I, which is the smallest. Then the medium one is angle H. And then the largest one is angle G. So that's that. We'll do something similar. This is the smallest. The red is the medium. And finally, the yellow is the largest. So I think my student watching agrees. That would be the shortest is QP, the medium is PR, and the longest is QR. All right, find the shortest segment. Okay, this is, in my opinion, the second most difficult one of the whole worksheet, unless there's some theorem that I'm forgetting. Either way, my reasoning that follows should sort of explain it, though. Shortest segment. Let's note that the angles are all the same in both of these triangles, right? So you have a 55-degree angle here. Well, you have a 55-degree angle in this triangle. You have a 65-degree angle in this triangle. Well, you have a 65-degree angle in this triangle. And you have a 60-degree angle in this one there. And you can see, obviously, that's the case with the other one. So what I'd like to do is a move that my student might be noticing I like to do a lot, which is to separate them, okay? Because that helps me analyze each one in a very focused way. So we have 65 here, 60, 55, 65, 60, 55. Now they both share this red side. which I'll call the shared side. Okay, that's the shared side. Now I want you to notice something. You see this blue 55 degrees? Isn't that the smallest angle of all of these? Yeah. So that makes this shared side the shortest angle, shortest side, pardon me, of this triangle. This shared side is the shortest side of this triangle. Now, when you look at this one, this angle is 65. Isn't that the largest angle of all three of these? Yeah. So doesn't that make the shared side the longest side of this triangle? So this shared side is the shortest side of this triangle, but it's the longest side of this triangle. That means that this triangle has to be basically smaller than this triangle. Okay. So once again, the shared side is the shortest side of this big triangle, but it's the longest side of this small triangle. So if we're looking for the shortest segment, just in general, of the whole diagram, well, obviously, the shortest segment is going to be the shortest side of the smaller triangle. Well, this is the smaller triangle. So what's the shortest side of the smaller triangle? It's obviously this one, because it's across from the 55-degree angle. Now, maybe again, there's a theorem that I could have used, but I don't remember what that is. So it's X, Y, okay? Either way, the way I explained it is better for your brain, okay? So hopefully that makes sense. The shortest segment is X, Y. So let's move forward. Okay, point G is the centroid. All right, the moment they say that, you know we can label it in the awesome way. So AE is 24. Okay, they're talking about how the red AE is 24. Now let's be very clear. That makes this part 8. This is 8. And this is 8. Cool. DG is 5. Okay. We have this blue median. This part is 5. That makes this 5 and that 5. Okay. CG is 14. Hmm. Hmm. CG 14. That's the green thing. And CG is 14. Okay. But we also know we could have divided this into things, into little pieces. So that has to be 7, and that has to be 7. So that's a 7, that's a 7, right? And that's a 7, right? Because they just told us once again, CG is 14. So that means that that could be 7 and that part could be 7, right? What's DB? Well, I have a feeling this is going to be totally easy. We already labeled everything, so that's 5 plus 5 plus 5, so DB is 15. So this is another example of how, at the end of the day, we didn't need to label the whole thing. Yeah, maybe you could just focus on the DG part, understanding that if they're asking for DB, be like, okay, I don't need all this other info. Just focus on the thing that has a D in it, and then kind of analyze that. Maybe you could do that on the test. I don't know if the test is going to be similar in that way. Number two, vertices are that find the coordinates of the orthocenter. Yeah, I mean that's another one that's XY coordinate plane-ish. Um, let's look at it. We have Um, Point at 2 comma 4, that's about here. We have a point at 10 comma negative 6, that's here. That's F. And another point at negative 4 comma negative 8. So that's about here. Um, and that's G. They want the orthocenter. Okay. Well, let's remind ourselves of what the orthocenter is, and that is um, the point of concurrency that has to do with the altitudes. Okay. So let's remind ourselves that an altitude is like starting at a vertex and dropping straight down in such a way that forms 90 degrees with this side. Okay. And the orthocenter is where all those altitudes cross each other. Now, for my student watching, this again might be another one where the teacher does not expect you to do it on the test because this is quite advanced, um, compared to a lot of the other problems, at least. Okay. So just be on the lookout for whether or not the teacher needs y'all to know how to do these. I will say that the good news is that you don't need to analyze three altitudes. You only really need two because if we could just draw like two altitudes, well, then we could just find out, where they intersect by using a system of equations, and then we would have our answer. Okay. Now I'm going to go ahead and do it. A part of me feels resistant because I'd be pretty baffled if my student was expected to do this based on what we've covered already. Um, but nonetheless, it would be a good exercise, I think, for people. So uh, the way to go about this is to recognize that an altitude sort of goes from a vertex and ends up being perpendicular to the opposite side. Now, what does that mean? That means that it has a negative reciprocal slope to whatever this slope is, okay? So in other words, if the red thing is perpendicular to the blue thing, well, the red line must have an opposite reciprocal slope to the blue thing. So that's one concept we're going to need, okay? Perpendicular lines have opposite reciprocal slopes. Another concept we're going to need is the slope formula. The slope formula is this. Hopefully my student remembers that. That's another concept we'll need. Now, another concept that is probably going to be useful is this point slope form equation of a line. Okay, now in this point slope form, the m is the slope, and sort of the red x1, y1 is this sort of point that happens to be on the line of interest. So the plan is to find the equation. Now we can kind of take our pick now. We can find the equation of this altitude, find the literal linear equation of that red altitude. We could find the equation of this green altitude, and then just find out where those two lines intersect. Now, let's start with the equation of the red altitude. Well, isn't the red altitude perpendicular to this black side? And because that's true, isn't it true that the slope of the red altitude is the opposite reciprocal of the slope of this black line? Well, yeah. So let's find the slope of the black line. The slope of the black line is -6 minus -8 all over 10 minus -4. And that is -6 plus 8 over 10 plus 4. And that is 2 over 14, aka 1/7. So the slope of the red altitude is -7 over 1, also known as -7. Now, we also happen to know a point that the red altitude goes through. It goes through the point 2 comma 4. Let's write that down. That is very useful information because now we have a point that the red altitude goes through, and we have a slope of the red altitude. Well, I just finished telling you there's a concept called point slope form, and you can use this to construct the equation of a line. Okay. How? Well, it's going to be such that here's your point, and you just plug it in here and here, and that's where your slope goes. So this is going to become y minus y1. Y1 in this case is the 4. In fact, let's label this x1, y1. So y minus 4, maybe I'll even keep it in red, equals the slope, which is this blue -7, times x minus x1. What's x1? That 2 right there, right? So that's the equation of the red altitude. Now let's clean it up a little bit. We could distribute this. We could say y minus 4 equals -7x plus 14. We could add 4 to both sides. That becomes -7x plus 18. Okay, so that is the equation of the red altitude. Let's find the equation of the green altitude. Well, when it comes to the green altitude, let's look at it. Isn't that green altitude perpendicular to this purple line? Yeah. So doesn't that mean that the slope of the green altitude is the opposite reciprocal of the slope of the purple line? Yeah. So what is the slope of the purple line? That's -6 minus 4 all over 10 minus 2. That ends up being -10 over 8, aka -5 over 4. Therefore, what is the slope of the green line? The slope of the green altitude is +4 over 5. Okay. Now, not only do we have the slope of the green altitude now, but we also have a point that we know that the green altitude goes through. It goes through -4 comma -8. So let's see. We'll write down our information here. We have a slope 4/5 and a point called -4 comma -8. And we can call that our x1 or our y1. And we can begin to construct the equation of the line by using our handy dandy point slope form. And that would be nothing more than y minus y1. In this case, it's -8 equals the slope, which is 4/5, times x minus x1, which is -4. Cleaning that up would be y plus 8 equals 4/5 times x plus 4. Let's distribute this in there. That would become 4/5 x plus 16 over 5. And let's see, we could subtract 8 from both sides. Now, finding a common denominator here would be a matter of multiplying it times 5 over 5. So that would become 4/5 x plus 16 over 5 minus 40 over 5. And then that would become 4/5 x minus um, 24 over 5. Okay. So that's the equation of the green altitude. So if we want the orthocenter, then we would have to find the intersection between this red altitude and this green altitude. We have the equation for the red altitude, it's right here. We have the equation for the green altitude, it's right here. So we could do a system of equations where we set them equal to each other. So the y equals 4/5 x minus 24 over 5 is one of them. And then we have y equals negative 7x plus 18 is the other. And at that point, we can recognize they both equal y, so they both must equal each other. So we can set them equal to each other, and that would be a matter of getting rid of this 5 that's on the bottom. The way I'm going to do that is to multiply everything by 5. You have to multiply everything by 5. That would cancel these out, which is a beautiful thing. On the left, we would be left with 4x minus 24. Over here, we would have negative 35x plus 50 plus 40, which is 90. Adding 35 to both sides gives me a 39x. Adding 24 to both sides would give me a 114. Okay, dividing both sides by 39 would give me 114 over 39. The top and bottom are divisible by 3, so that would become 38 over 13. So believe it or not, that is the x-coordinate of the orthocenter. Now, in order to find the y-coordinate of the orthocenter, you then have to pick one of these two equations. It doesn't matter which one. I'm going to pick this one because it looks nicer. And we are going to plug in 38 over 13 for x. So this becomes negative 7 times 38 over 13 plus 18. Negative 7 times 38 is negative 266, and that's all over 13 plus 18. Here we could get common denominator by multiplying 18 by 13 over 13. It would be true that um, 18 times 13 is 234. So that's 234 over 13, keeping that common denominator on the bottom and combining the numerators gives us negative 32 over 13. So that is going to be the y coordinate of the vertex of the orthocenter. So they had asked for the orthocenter, the coordinates of the orthocenter. Well, here they are. It would be 38 over 13, comma, negative 32 over 13. Now, once again, for my student watching, double check that one, okay? Make sure that you have to, whether, make sure you know whether or not you need to know that. Okay, looking at this right here, this is probably going to be a friggin' piece of cake compared to that last one, right? If JL is a median, find the value of X. Okay, well, a median is such that it emanates away from the vertex in such a way that cuts this in half. So this is just laughably easy. You set these equal to each other. Um, that would become 32, right? So, good Lord. Compound inequality for the possible measures of L. So, according to the exterior angle inequality theorem, we know that whatever L is, I mean, it's got to be less than the exterior angle, right? So we could write that down. L is less than 146. Now, is there anything that we know that L has to be greater than? The only thing I could think of is that L has to be greater than zero, right? If L was zero, then it wouldn't even really be an angle in a triangle. So L has to be greater than zero. Now, when they say compound inequality, what they really mean is put L in the middle and have the symbols looking like that. So, and then just kind of make sense out of it based off of what we did. L is less than 146, so you can put the 146 here, but it's simultaneously greater than zero, so the zero can go there. Okay. I think that's all we need to know for that. Um, L has to be greater than zero. I can't think of another number that L definitely has to be greater than, other than zero. So I think we're good. Problem number five, list the angles in order from smallest to largest. Okay, S for small, M for medium, L for large. Clearly, S, M, L, right? So angle H, angle I, and angle G. Right, list the sides of PQ or R in order from shortest to longest. Okay. Well, S for short, M for medium, L for longest. S, M, L. I think we all get that, right? So that's QR, QP, and PR. That name the shortest and longest segments. Hmm. I'd say this is fairly similar to a previous one. And once again, I would rather um, analyze it by separating the triangles. So we have the shared side, once again, is the red side. We then have this W, X, V, X, V, Y. And the red one is the shared side. Now, we can label these, of course, and we're just going to use something like common sense. This red shared side is the longest side of this triangle, right? Because it's across from the 72. Yet, this red shared side is the shortest side of this triangle. So this triangle must have a longer long side. I mean, that's one way of thinking about it too. Okay. So what's the longest side of this triangle? The longest side of this triangle has to be longer than the longest side of this triangle. So the longest side of this triangle is this purple right here. Okay. So that um, is the longest side. But we also need the shortest side. Now, the shortest side of this triangle is XV, but XV is the longest side of this triangle. So the shortest side of this triangle must be the shortest side out of all of these. So the shortest side of this triangle is VY. So let's remind ourselves that they were asking for the shortest and longest segments in the whole diagram. Well, what we just discovered is that the purple one is the longest segment in the whole diagram, and this green one is the shortest segment in the whole diagram. All right, so you'd have to label that the longest is WV and the shortest is VY. So that's that. Write the assumption you would make to begin an indirect proof of the statement. Okay, so this is another one that I'd be very surprised um, if the teacher wants my student to do it. Indirect proofs are such that I think you begin with assume otherwise. Um, you would say assume otherwise, that if 2x plus 6 equals 12, then x does not equal 3. And then you would kind of investigate that situation. And if you could prove that that's impossible, then it would be the case that x equals 3, something like that. Okay. So to me, that is yet another example of something of a higher level concept. In fact, this concept is college level, so I'm not really sure why the teacher is giving you that. Let's see. Mm, Problem number 9, determine whether 8, 4, and 2 can be the lengths. Okay, good. Back to some familiar ground. Is 8 less than the sum of these? No, it's not. So this cannot be a triangle because 8 is greater than 4 plus 2. So already that violates the triangle inequality theorem. Okay. So you could say literally it violates the triangle inequality theorem. Okay, once again, the higher level concept of indirect proof. Remember, this always starts with the sentiment assume otherwise. And you kind of imagine sort of the negation of this or the negation of the conclusion at least. So the three angle bisectors of a triangle are concurrent. So I would say assume otherwise. The three angle bisectors of a triangle are not concurrent. Okay. So that is a way to start your indirect proof by assuming the opposite of what they're saying. Okay. Write and solve an inequality for x. Yeah, so this is the hinge theorem once again. Notice how this angle, this part of the top part is equal to this part. Notice how this green part is equal to that green part. So you have an angle sort of on the top that's giving birth to this six. So this angle is opening to that six. Whereas this angle down here, you know, is opening to this 10, right? And we know that the blue is equal to the blue and the green is equal to the green. So the fact is, this angle is opening to a longer side length. So that means that this angle has to be greater than whatever this angle is. And that's the key. They want you to simply write and solve an inequality. Okay, so we know that 12x minus 31 has to be greater than 3x minus 4. but then they want us to solve it. Subtracting 3x from both sides gives us this. Adding 31 to both sides gives us this. Dividing both sides by 9 gives us this. So no matter what, the whatever x is, because of this situation, x has to be greater than 3, no matter what. All right. So that's how you do that. That's a relatively challenging one, but it's within the scope of what we've been doing. Anyway, that was pretty wild. And hopefully that was helpful. And I will talk to you all later.